Hi, before here, let's talk about rotational motion. We're a little bit familiar with this idea of rotational motion already. Let's formalize it. Maybe it's not right. Okay, when we talk about rotational motion, what do we really mean? If we define x and y coordinate system, the rotational motion is just an object moving around in a circle. Like so, we can define a few things to characterize, isn't that certain?
The radius r of the circle, the angle theta between the line to the object and the x-axis. We can also talk about the angular speed of the object, and we can also talk about the alpha, the angular acceleration. These are the important variables theta, omega, and alpha.
And in fact, the equations that describe rotational motion are really identical to the ones that describe linear motion. We are just changing the variables. So for instance, when we're talking about linear motion, we said we're going to x, and we're going to have v. We know that v is dx over dt, and we're gonna have a. We know that a is dv over dt.
And now I'm rational, we're gonna do the same stuff. We just change the variables, so instead of x, we're gonna use theta. What is omega? Omega is d theta over dt. What is alpha? Alpha is d omega over dt. Omega is called the angular speed. Alpha is called the angular acceleration. Okay, theta is of course the angle, and typically we use theta in radians. Now if we're making the substitution theta and radians, we also realize that we have a whole set of equation, the kinematic equation, which govern motion.
For instance, this one is x final equals x initial plus vx initial times t plus 1/2 a sub xt squared. That's one of those provisions, and we can write the corresponding rational equation like this. Theta is equals theta 1 plus omega initial times t plus 1/2 alpha squared. All the math is exactly the same. Now there is a caveat with the kinematic equation. The kinematic equation applies when you have constant acceleration.
If your acceleration is not constant, then you cannot use the kinematic equations. And so you have to be careful when you write this equation down over here. The caveat is constant angular acceleration alpha. But if you have constant alpha, you can use all of this kinematic equation that we developed before. Now we also learned a little bit about some other terms in linear motion like work. Let's see how that applies to rotational motion work W.
We also learned some other term in linear motion. Let's see how that applies in rotational motion. Work, or W, is said was the integral of f sub x dx, where we're gonna integrate from some initial position to final position. We wrote it with a dot product before, but this is the same information here as is the x component of the force, which is what the dots. The dot product of it picks out the x component. In rotational motion now, we're gonna integrate from theta to fit it at half. We're not dealing with a force anymore. We are in fact dealing with a new term torque, and we have to integrate over angle. So this thing tau is what we call torque. Torque is to rotational motion and force is to linear motion. So if I take a wheel and I put a torque on it, it will angularly accelerate.
We also know that when things are moving, they have kinetic energy. The kinetic energy that we write with the capital K is just 1/2 mv squared. And if things are rotating, they also have energy. And we call that rotational kinetic energy 1/2 I omega squared. And now we've introduced yet another term, I was, which is the moment of inertia. So in linear case, objects have mass, and if they're moving at speed v, then the kinetic energy. And in the rotational case, objects have moments of inertia. And if they are rotating at omega, then they have rotational kinetic energy.
And so, you can actually store a lot of energy in a rotating things right after you have a big flywheel in a bus. When you come to stop, instead of applying bricks, which is really just a fraction, right? Bricks to bricks pad hitting a piece of metal, when the metal heats up and it loses all the energy as heat. You can take a different approach, which is when you spin up a flywheel and now you have a big rotating disc inside the bus, and when you start the bus up again, you can tap on that energy and suck it back up.
And so, they actually do use these giant rotating flying wheels, buses and trains, not in a smaller cars, because they're typically big and heavy wheels. But it's a way to transfer energy between systems. We also talk a little bit about power.
One of the things we said about power was power in a linear case is equal to force times velocity, and you apply a certain force to get your car moving, and v, the velocity, is how fast your element was. So the power used goes like F times v. In the rotational case now, we don't use F anymore. We use torque, and we don't use v anymore. We use angular velocity omega. Alright?
So, that's how much more power is in rotational systems. The whole point here is everything that we've learned so far is in linear kinematic. If you just change variables, and so this is the trick of sorts of convincing yourself that there is nothing that complicated. Here, I just have to start using some different letters, and these in rotational are apart. Usually, G and tau and omega and alpha theta, and these over here typically in